In this module, we'll cover equilibrium constants and pH. Here we see the dissociation of water going to hydroxide ion and protons. This happens very quickly. Equilibrium is assumed when the rate of the forward and back reactions are equal, such that when we observe the concentration of products and the concentration of reactant, that stays constant over time. So we've discussed this in terms of a mass balance as a steady state. When we consider equilibrium, we also observe that the concentration does not change with time, but what is actually occurring is continuous forward and back reactions of those molecules. Experimentalists can define something called an equilibrium constant, K, for any given reaction. This cannot be calculated, but must be determined empirically through experimentation. We will use tables in previous work from experimentalists to find equilibrium constants and use these to predict concentrations at equilibrium for a water system. Here is an example with reactants A and B going to products C and D, where sub A, sub B, sub C, and sub D are the number of moles associated with each compound. For any reaction, we can define an equilibrium constant, K, in terms of the molar concentrations of the products divided by the molar concentrations of the reactants, two exponents. There are a few rules when writing an equilibrium constant expression. We would always say that the concentration of water is 1. If compound C were a solid, such as calcium carbonate, we would also say that the molar concentration equals 1. You will need to commit this rule to memory. So K is found experimentally, but we can write an expression, a mathematical expression, for the molar concentrations that are equal to K. If we were to write the mathematical expression of the equilibrium constant K, we would say that the products, the molar concentration of proton multiplied by hydroxide ion, divided by the molar concentration of water, which is 1. Experimentally, chemists have found that K is equal to 10 to the negative 14. Now, many of you are very familiar with this equilibrium constant, but may have never considered it in this form. Here is a general expression for pH. pH equals negative log of the proton ion. You can also write pOH, which is equal to negative log of the hydroxide ion. Now, many of you have worked with pH in a chemistry lab and know that the pH is always written into a scale of 1 to 14. I'd like for you now to appreciate that the 10 to the negative 14 equilibrium constant for the dissociation of water is what provides us the scale of 1 to 14. If you look at this expression of the equilibrium constant and you take each side of the equation by the log, you would see that negative 14 equals log of H plus log of OH. This is typically written as 14 equals negative log hydrogen minus negative log hydroxide, or 14 equals pH plus pOH. This rule is extremely useful when converting between the given pH, which is easily measurable of a solution, to the hydroxide ion concentration and the hydroxide ion concentration present in that solution. In this example, you are given the pH of a system of 5, and you're asked to find what the molar concentration of hydrogen and hydroxide ions are. When given the pH of a system, it is very simple to also find the pOH of the system, as 14 equals pH plus pOH, and therefore the pOH is equal to 14 minus 5 equals 9. Now pH is also equal to negative log of the hydroxide ion concentration. This negative could be brought over to the left, and if you take each side to the base 10, you're left with hydrogen ion equals 10 to the negative pH. Likewise, hydroxide ion is equal to 10 to the negative pOH. So in this problem, when the pH is given as 5, you should also be able to interpret that as the molar hydrogen ion concentration is 10 to the negative 5. and the hydroxide ion concentration is equal to 10 to the negative 9 moles per liter. In your homework, you would not need to show this work. I've done this for you once, but you can quickly skip from the given pH to the molar concentration. One type of equilibrium reactions that are very important to water chemistry are precipitation reactions. We will often, in environmental engineering processes, precipitate out dissolved impurities. A generic form of a precipitative reaction is when given a solid, or precipitate, that would dissolve into two forms of the cation and the anion. And by convention, the precipitate or solid form is always written on the left-hand side of a chemical reaction. Now, the solubility of different substances vary greatly. For instance, salt, sodium chloride, is readily soluble, and so the equilibrium constant for salt would be very high. On the other hand, rust is highly insoluble, and so the equilibrium constant for rust would be very low. The most common precipitative reactions that are used in water treatment can be found in this table in your book. Aluminum phosphate, calcium carbonate, ferric hydroxide, ferric phosphate, and magnesium hydroxide. These are used for various applications which we will cover throughout the semester. Now, an equilibrium constant is always denoted by big K. But sometimes there's a subscript next to the equilibrium constant which denotes what type of reaction is being discussed. KSP, for instance, is a solubility reaction or precipitation reaction. Ka is referred to sometimes as an acid dissociation reaction. These different forms of K are no different than the generic form, in which K is equal to the products of the reaction divided by the reactants. And you should be able to write that generic form for any type of solubility acid or any balanced reaction provided. Because it gets cumbersome to write 10 to the negative all the time, many tables will express a pK instead of a K. pK is simply equal to the negative log of K, just as pH is negative log of the hydrogen ion concentration. So in this table, when given a pK of 11.25, you should be able to quickly interpret that as the Ks being equal to 10 to the negative pKs. In this example, we're asked to compute the concentration of copper ion that would dissolve at 25 degrees Celsius at pH 8 and pH 7. You're asked to assume that the solubility is controlled by the copper hydroxide solid. This example is very pertinent to something called the lead and copper rule of the Safe Drinking Water Act. To begin the problem, we want to write an expression for the equilibrium constant K. So K equals the copper molar concentration times the hydroxide concentration to the molar amounts, so 1, and then the hydroxide would be squared. And this would be divided by the solid precipitate, which would be given the molar concentration of 1. We want to solve this chemical equation twice. First for a pH equal to 7, and then for a pH equal to 8. Now we should be able to quickly know that when the pH is equal to 7, the pOH is equal to 14 minus 7, or 7. And when the pH is equal to 8, the pOH is equal to 6. So given this, the hydroxide ion concentration is equal to 10 to the negative 7 molar at a pH of 7, and a hydroxide concentration equal to 10 to the negative 6 molar at a pH of 8. So we would solve this chemical equation twice. Once for a hydroxide ion concentration of 10 to the negative 7, and once for the concentration of 10 to the negative 6. So at pH 7, we see that the copper concentration is equal to K divided by the hydroxide ion concentration squared is equal to 2 times 10 to the negative 19 divided by 10 to the negative 7 squared. And that is equal to 2 times 10 to the negative 5 molar. At pH 8, we see that the copper concentration is equal to 2 times 10 to the negative 19 divided by 10 to the negative 6 squared, or 2 times 10 to the negative 7 molar. Now, understanding that copper is toxic to humans, you can see quickly that at a pH of 7, the copper concentration is much higher than at pH 8. Now, it may be easier for you to consider the concentrations in terms of milligrams per liter instead of moles per liter. It's a simple conversion using the molecular weight of copper, or the atomic mass of copper, which is equal to 63.5 grams per mole. So when we do that, we see that a 2 times 10 to the negative 5 mole per liter concentration times 63.5 grams per mole yields a final concentration of 1.3 times 10 to the negative 3 grams per liter, which is equal to 1.3 milligrams per liter, and that is at pH 7. At pH 8, we would use the same conversion, but we start with 2 times 10 to the negative 7. That yields 1.3 times 10 to the negative 5 grams per liter, which is equal to 13 micrograms per liter. It is more obvious, perhaps, that at pH 7 you have a much, much higher concentration of toxic copper than at pH 8. I'd like for you to consider this because when we get to Safe Drinking Water Act, you'll see that there is a minimum pH that water distribution systems need to maintain to prevent dissolution of copper in your pipes. Now, before we end this module, I do need to state a couple of disclaimers about precipitation and equilibrium. The solubility reactions for metal carbonate and metal hydroxide complexes involve carbonate and hydroxide. Therefore, the pH of a solution greatly affects the equilibrium concentration of free metals in solution. This should have been obvious with the copper hydroxide example just shown. When you use an equilibrium constant to solve for concentrations present, you are assuming equilibrium has been reached. In reality, the dissolution of solids can be very slow, and equilibrium may never be reached. This is particularly true in water distribution, where water is often flowing. So when you use an equilibrium constant to solve for those concentrations, you may be overestimating the actual concentration that is reached. Finally, these calculations assume that the metals are free once they are released into solution. But in reality, water is full of many ions, and one freed up metal ion may complex with another anion in solution. For this reason, equilibrium models in water chemistry can become very complicated. In this course, we'll stay with fairly simple examples, and then, if you'd like, you have the opportunity to take water chemistry.